Hi everyone. Thank you so much for coming to our talk. My name is Karl, and I'm excited to present our recent paper entitled Cryptonite, a framework for flexible time series secure aggregation with non-interactive fault recovery. Our motivation for studying this problem is quite simple. In modern times, as many of you know, the ability for a third party to perform analysis on a group of users' private data is becoming more and more important for a variety of business and/or research tasks. However, in modern times, these data analysis frameworks often have to be able to process over millions of queries with little to no latency in order to be deployed in the real world. In spite of this speed requirement, many of these frameworks also have to make sure that they follow the guidelines put forth in a variety of legal agreements such as HIPAA, etc. In a situation where this is being done on an IoT device or a mobile device, being able to satisfy these requirements despite a limit on computational resources is a challenging problem. However, even though this is a hard problem to solve, there are existing techniques that have been developed to help solve this problem. One of the most popular and most well-known is private stream aggregation, which allows an aggregator party to collect the sum of a group of end users' private inputs for a particular timestamp. In this protocol, only the final result or sum is learned by the aggregator, but the aggregator cannot learn which individual user input which particular value. This is essentially done by having a group of users encrypt their plain texts in a special way such that when they're combined together on the aggregator side, they are able to recover the final aggregation, but nothing else. Even though PSA is a powerful technique, in real life it may not be useful to be practically deployed because it struggles to support fault tolerance. Existing solutions can't provide fault tolerance without placing trust in the aggregator in some form. This might not be practical in real life. We solve this problem with our framework, Cryptonite, by developing a set of techniques that allow any PSA scheme to support non-interactive fault tolerance without occurring additional significant overhead. What we mean by non-interactive fault tolerance is the ability for an aggregator to recover from faults dynamically on the fly without requiring extra messages to be sent to or from faulted users or any trusted party. Existing solutions are focused on the interactive fault tolerance case, which does require these additional messages to be sent. Importantly, we don't require users to trust the aggregator. So for our Cryptonite paper, we have a few major contributions. The first big one is we found trust issues in existing security definitions related to PSA and defined our own new, stronger level of privacy that accounts for faults. We call this fault tolerable aggregator obliviousness. We also developed a new formal framework for PSA that incorporates faults into the design, and we developed general techniques that can extend any existing PSA scheme to support our non-interactive fault tolerance definition. We also constructed the first protocol that provably reaches our new level of privacy that we described, and we do this using trusted hardware, specifically a trusted execution environment. With this implementation, we were able to demonstrate improved scalability and communication over existing work. As I mentioned before, there is existing work that tries to tackle this problem. However, to support fault tolerance, what is done is the aggregator must send a request to some third party that they need the third party to provide either user keys or ciphertext so that they can complete the aggregation calculation and determine some partial sum. The problem with this is, in real life, it might be difficult or impossible to find some trusted party that can do this without compromising individual users' privacy if the aggregator misbehaves in some way. I'll briefly summarize the existing primary two families of fault-tolerant recovery techniques. The first has the aggregator ask some trusted third party to provide information so that they can recover from a fault. Usually this is in the form of ciphertexts or keys, etc., that could leak user privacy. Also, another technique allows users to buffer future inputs and send multiple inputs to an aggregator ahead of time, so if at a future timestamp they don't respond, the aggregator already has a ciphertext corresponding to that timestamp. These fault recovery techniques may not be practical in the real world because they overly rely on trusted parties or trusted behavior on the part of the aggregator. For instance, if the third party that is ostensibly trusted behaves in a malicious manner, or if the aggregator simply lies to the trusted party about who faulted, the aggregator can recover all the private information that is associated with the honest participants and launch a residual function attack to recover the individual's private data. For those of you that may not be familiar, the residual function attack is a situation where an aggregator can compute the same function over different inputs, compute the difference between the final outputs, and infer individual values inputted by different users. We can also see that the other family of fault recovery techniques where users buffer inputs is similarly vulnerable, as the aggregator can compute multiple functions over different sets of inputs. The serious concern is that current protocols are still technically secure under existing standard security definitions. As a result, we need a new, better definition of security. Although there's more technical details in the paper, I'll briefly summarize our new security definition that we call fault-tolerable aggregator obliviousness. We say a PSA achieves our definition if the aggregator only learns one sum for every time period, even if a group of users fault. If, without knowing the aggregator's own personal secret key, no user or malicious aggregator can learn anything about the encrypted data, even if users collude. And thirdly, if the aggregator colludes with some subset of the users to behave maliciously, or if some amount of encrypted data is leaked, the aggregator learns no extra information about any honest participants' data. This better captures the requirements needed to protect against the residual function attack, since at least two separate function evaluations must be completed by an adversary for the attack to be successful. Now that you've seen our new security definition, I'll also briefly highlight our new framework that allows any existing PSA scheme to achieve this new definition of security. The setup phase is fairly standard, and there hasn't been many changes there where we distribute private keys. Also, the encryption is fairly standard, and we have every user use a private key to encrypt their value and send it to the aggregator. The most interesting part, I would say, is the fault recover component. We formalized the fault recovery mechanism here so that we can better enforce that protocols will not be vulnerable to the residual function attack. Our framework supports the same general functionality as the previous frameworks, but also allows the aggregator to recover the needed information from users who fault without allowing a malicious attack to take place. Even after the aggregator receives all the ciphertexts, they can only optionally invoke our fault recovery mechanism, and this mechanism verifies that the aggregator does not lie during the fault recovery. If they do lie, we can abort and prevent someone's privacy from being leaked. Once this is completed, then we can simply aggregate and decrypt as normal in standard PSA techniques. Our system is summarized in this figure. For our deployed system, we used Intel SGX. This is a set of new CPU instructions that can be used by applications to set aside private regions of code and data. This allows developers to protect sensitive data from unauthorized access or modification by malicious software running at a higher privilege level. Importantly, it lets external users cryptographically attest that the Intel SGX software is running on a system and will protect their data. So basically, in our protocol, a group of data owners will encrypt their private data and send it to an untrusted aggregator. This aggregator will send the encrypted data into an SGX enclave to perform some verification operations. Once this is done, we'll send it out to an untrusted GPU along with any necessary recovery information, where in this more powerful setting, the data can be aggregated to get a final result. The first part of our protocol is known as the setup phase. First, every user will perform that attestation process we described earlier to make sure SGX is working properly. After this is done, the Intel SGX will perform all of the key generation in a secure manner after choosing a secure random generator of a group G and creating n+1 random secrets, such that if you add all the secrets up, they sum to 0. Once this is done, the generator G is made public, and the aggregator obtains their own personal key, which we denote sk sub 0, and each participant I is sent their own individual secret key, which we denote sk sub I. The next phase of our protocol is known as the encryption phase and happens at the user end. Every user will encrypt their individual private plaintext value x during a certain timestamp t s by using the following formula. This formula is well known within the field of PSA, but I'll give a quick overview of it here. It's typically defined over elliptic curves. Basically what you do is you take the generator point and you raise it using scalar multiplication to the plaintext value. Once this is done, you use a cryptographic hash function to take a hash of the timestamp, which maps the timestamp using the hash to an elliptic curve point. Once you have that point, you perform scalar multiplication using your secret key. And once that's done, you add those two individual points together to create the ciphertext. After the encryption phase, the users send their ciphertexts to the aggregator, and the aggregator has the opportunity to utilize the fault recovery mechanism. Essentially, after a particular time period associated with a timestamp has ended, within the Intel SGX, we can input every ciphertext that was received and record inside of the Intel SGX which users failed to respond. An important thing to note is because we're doing this inside the Intel SGX, it's not an opportunity for a malicious outside attacker to tamper with the fault recovery process or otherwise learn an individual user's private input. Note that since the Intel SGX generated all the user's secret keys during the setup phase, if a user does not respond, it can compute the ciphertext using that formula we discussed before associated with a plaintext input of 0 for every user in the set J, where we use J to denote the set of all the users that do not respond or otherwise fault. After the fault recovery phase is over, the aggregator has everything that it needs to compute the partial sum over the users that did respond within the time period. However, because we used our fault recovery mechanism inside the Intel SGX, this removes any opportunity for the aggregator to behave badly and try to steal secret private information about an individual user's input. Essentially, to perform the final aggregation, the aggregator uses the aggregator secret key that was generated during setup but is kept secure within the Intel SGX to compute the aggregation over all of the ciphertexts that were generated. Once we get this final result V, we can decrypt using a standard technique from PSA, which is to leverage Pollard's lambda method to determine the sum. Please note that this is only practical in a situation where the plaintext space size is small. That essentially sums up our basic protocol in a nutshell that allows us to achieve efficient private stream aggregation with non-interactive fault tolerance. Please note that we only discuss the basic scheme here, but in the paper we discuss a slightly more efficient scheme that is capable of migrating some of the computational work outside of the Intel SGX and onto potentially more powerful hardware such as a GPU, etc. Now, we did run some experiments in C++11 to simulate having thousands of users run our protocol, as is sort of the standard treatment in the literature of PSA. For these tests, we used an Ubuntu workstation with an Intel i7 core, and we used Intel SGX version 2.9.1. Here we summarize our results from these tests. We highlight the performance of our basic protocol when compared to our improved protocol that we discuss in the paper. The key takeaway is that if we migrate the aggregation outside of the Intel SGX, the aggregation time is noticeably shorter than if we perform the aggregation inside the Intel SGX. This makes sense because there is some overhead from computing inside of the Intel SGX. However, this does slow down our recovery time if a user faults because we have to do additional expensive paging in and out of the enclave, which adds overhead. However, the big takeaway is our results show that the overall computation time scales well in the presence of a large number of users. And for instance, our protocol only takes about a second to finish when there are 1,000 users, assuming the setup step has been pre-computed. We also notice in the lower charts that this means, since we can pre-compute those dummy ciphertexts that are associated with an input of 0 for use when performing non-interactive fault recovery, even when many thousands of users fault, the additional recovery time is minimal and is often under 30 seconds, which is practical. We also experimentally evaluated our work when compared to some other baseline techniques within the realm of PSA and ran some simulations to compare our scheme to two state-of-the-art PSA schemes. The binary scheme, which has users buffer their inputs that they send to the aggregator to allow for fault tolerance, and also the circle scheme, which has the aggregator communicate with a trusted third party to support a form of fault tolerance. Notice that the circle scheme is slightly faster than our scheme during encryption and aggregation, as they leverage a more efficient cryptographic primitive than us, specifically the HMAC. This means we can conclude that although our encryption scheme scales well in the presence of a large number of users, we're still about 2 to 6 times slower than the circle scheme if no users fault. However, we offer the most efficient fault recovery of the schemes since we are able to efficiently interact with an onboard trusted execution environment, Intel SGX. Unlike both of the other schemes, we can recover from faults without having to buffer ciphertext, which causes increased communication overhead, or having to have additional rounds of communication. In addition to this, we can support a stronger level of security that does not require that we communicate with a trusted third party to recover from a fault. And so, to summarize our contributions with our Cryptonite paper, we first defined a new level of security for private stream aggregation, PSA, in the presence of faults and malicious adversaries. Now, after we described our new framework for PSA that accounts for fault tolerance, we developed the first protocol that can provably reach our new security level definition. We also ran some simulations to demonstrate that our protocol reaches high levels of scalability and communication efficiency over existing work, while simultaneously supporting a higher level of security and better fault tolerance overall. We stress that our techniques are general and can extend to any other PSA scheme to allow it to achieve non-interactive fault tolerance. Thank you for listening in to our talk, and this concludes the presentation.